But this led me down an even bigger rabbit hole because it turns out this simple fact is the basis for testing whether or not a number is prime in the fastest possible way that humans know. So this video is a follow-up to this last video on Pascal's Triangle shown here, and it's all based on one comment that someone left that sent me down a rabbit hole. So this comment says, fun fact, the fact about the prime rows of Pascal's Triangle is actually an if and only if. So in this video, I explained that if n is a prime number, then the nth row has zeros inside. And that's what was proven in the video. That's what caused all these fractal patterns to appear. And here is the example. When n equals 5, you look mod 5. So you take everything, you look at the remainder when you divide by n, and it's all zeros in the middle for prime numbers. And that's what causes these fractal patterns to repeat all over. But the user, the person who left the comment, actually said this is an if and only if. It goes both ways. So if you have all zeros, if you're working along and you look at some row and it's all zeros in the middle, mod n, then actually it must be that n is a prime number. Okay, and this is, a fun little fact. What I did in the video was only halfway. Maybe that's it. But this led me down an even bigger rabbit hole because it turns out this simple fact is the basis for testing whether or not a number is prime in the fastest possible way that humans know. So this simple thing, checking to see are there all zeros in Pascal's Triangle, you have to soup it up quite a bit, but it is the basis for this amazing result, which is proven in the Annals of Mathematics. So Annals of Mathematics is this really high-level journal. It's the best possible math journal, basically. If you publish a paper in Annals of Mathematics, it's a really important, serious result. And this paper has a really simple title, Primes is in P. That's the name of this paper. And it's just saying, checking whether or not a number is prime, here is an algorithm to do it, which is polynomial in the log of the number. You can tell a paper is good when they have a really short abstract like this. We present an unconditional, deterministic polynomial time algorithm to determine whether a number is prime or composite, a one-sentence abstract. And it all starts with this simple Pascal triangle thing. So I want to read you this really fun part of their paper where they made a section called the idea. And the idea is based on the following identity. And the identity is written in algebra, but I promise you this identity is just a fancy version of what we had in Pascal's triangle. So they're saying you want n is prime if and only if x plus a to the power n equals x to the n plus a mod n. So when you look at the remainders divided by n, these two things are equal if and only if n is prime. And that is exactly what we had over here. Why is it exactly over here? Because the rows of Pascal's triangle are actually the polynomials x plus 1 to the power n. So for example, this row, when n equals 2, 1, 2, 1 is actually the coefficients of x plus 1 squared. X plus 1 squared is x squared plus 2x plus 1. And if you read off the coefficients, they go 1, 2, 1. In the nth row, over here, you have x plus 1 to the power n. And x plus 1 to the power n, we saw in our video that it is all zeros in the middle. And all zeros in the middle means what is left over? Well, the only things are the 0th entry and the nth entry. The 0th entry is x to the power 0, which is a 1. And the nth entry is x to the power n. And so x plus 1 to the power n, that's the entire row. But because we have all these zeros in the middle, looking mod n, we know x plus 1 to the power n is equivalent to 1. Let me write it like this. 1, that's the 1, 1 over here, plus x to the n. That's the x to the n over here. And that is all when you look mod n. So this is a great algebraical way of writing down this simple fact we saw, that n is a prime number if and only if you have all zeros in the middle. That's exactly the statement they are using here. They point out you can actually replace the 1 with any number a, as long as a is coprime with n. But the Pascal's triangle version, straight up classically, is the case a equals 1, and they say you can check any other a you want. Okay, this is the basis for a simple test you can do, right? We're going to compute the n rows of Pascal's triangle, and then check if it's all zeros. And I implemented this in Python. So here is some Python code that computes Pascal's triangle. So generate Pascal's triangle, and it does it all in NumPy, so it's pretty fast. And it uses this np.roll command, so I can tell you exactly how it's working. np.roll is a command to shift everything over by 1. So you take the previous row, you shift it over by 1, and you add it to itself. So for example, if you had 1, 2, 1 as the last row. You shift it over by 1. You go 1, 2, 1, and then you add up the rows. Then you get 1, 3, 3, 1. That's the next row of Pascal's triangle. So that is how this one works. It's adding rows to itself, and it just does that a bunch of times. And then you end up with these beautiful plots. So there's also a function to plot it, which centers everything, and you get these nice pictures that were like what I had in the previous video, which were animated versions of these things. Okay, so there's 2 and 3, and you can get all these pictures, and you can get like big ones. So here is one mod 9 for some huge value, the first like 1,000 rows almost. Okay, so this is the code. And now that you have this code, you can use it to test if things are prime. And the way you test is you look at the nth row. So here is a test, n equals 91. Is 91 a prime number or not? Let's find out using Pascal's triangle. We make the triangle. We take the last row. So triangle of -1 gives us the last row. And then let's look at that value. And here is triangle of -1, the very last row over here that is plotted right at the bottom, the 91st row, mod 91. And you can see that there's a bunch of non-zero numbers. There's 1, then a bunch of zeros, but then a 13. And that's because 91 is not prime. 91 is 7 times 13. 13 is a multiple of it. So we can test just by checking this row if things are prime or not. And you might say, okay, this is like really slow. Like you got to do a lot of work. You got to add up the rows n times to get the answer. But actually there's a faster way to do it. And that's what I wrote over here. A faster way to generate only the nth row. So if you suppose you want to make the nth row, you want to figure out what is going on in row number 11. Row 11 only. So you could generate every single row, start at 1, then 2, then 3, then 4, all the way up to row 11. That would be a lot of work. Instead, what you could do, instead of generating the next row, I'm going to generate the doubled row. So I'm going to start with row number 1. This is row 1. I'm going to double 1 to get 2. That's row 2. And I'm going to skip. I'm never going to generate. We're going to skip this one. We're going to skip 3. And how am I going to skip 3? I'm going to double row 2. And to double row 2, what I do is I add row 2 to itself. So I take 1, 2, 1, and I'm going to combine that. In some sense, I'm going to square it. I'm going to square it. I'm going to put a star square. And that's because what I'm doing is I'm convolving it with itself. 1, 2, 1 with itself is going to give 1, 4, 6, 4, 1. So this is a convolution with itself to give 1, 4, 6, 4, 1. And you can also think about this as we had x plus 1 squared. Instead of going to x plus 1 cubed, which would be the third row, we're going to skip row 3 and go straight to x plus 1 to the 4 by multiplying it by itself. That's row 4. And then to go from 1, 4, 6, 4, 1, we're going to skip all the next rows. We're going to skip 5. We're going to skip 6. We're going to skip 7. We're going to go right to 8. We're going to go all the way up to row 8. Row 8. And row 8 you can get by doing 1, 4, 6, 4, 1. Square convolve it, so convolve it with itself to get the next 8th row. And this is like getting x plus 1 to the power 8 by starting with x plus 1 to the power 4 and multiplying it by itself. So multiplying this polynomial is the same as convolving the list of numbers. And so you can skip rows 5, 6, and 7 to go straight to row 8. Okay. And now you have row 8. If we were going to double it again, we would skip all the ones up to row 16, and we would just calculate row 16. But we actually wanted row 11, right? So if we were working to calculate row 11, we could take row 8 and get it. How are we going to get row 11 from what we have so far? Well, row 11 is 8 plus 2 plus 1. And we calculated what was going on row 1. We know that. That was something we did. We know what happened on row 2, and we know what happened on row 8. And if we convolve these 3 lists of numbers together, 1, 1 with 1, 2, 1 with 1, 8, 28, and so on, we will get row 11. And this is really like combining x plus 1 with x plus 1 squared with x plus 1 to the power 8, which are all things we calculated. By combining them, you can get x plus 1 to the power 11. And combining in polynomial land means multiplying, but in list of numbers lands means convolution. And that is what this code does. So if you want to check it out, if you want to see some NumPy code, you can check it out. And what we're doing is calculating all these things by doing the convolution of all the powers. P2 stands for powers of 2 with themselves. And we do it a bunch of times. Okay. And one extra thing we can do, so I'll show you, here's a little polynomial. The test is we generate the nth row. we can stop at the square root of n. So instead of generating the entire row, we can just generate the first square root of n entries. So let's go back to the picture over here. If you want to check if 11 is prime, for example, you don't actually need to check this entire row. You can just calculate the first little bit, because if it has a factor, that factor must appear somewhere in the first square root of n rows. So this is our Pascal triangle is prime check. We calculate the first little chunk of the nth row of Pascal's triangle, mod n. So we always take things mod n as we go to keep things simple. And we just check, is it all zeros? And all zeros means, okay, ignoring the 1 in the front, right? There's always going to be a 1 on the left side. We're going to ignore that and just check if everything else is all zeros. So that is our way to check using Pascal's triangle, is prime Pascal. And you can compare that to is prime naive. Naive just means I'm doing it in the simplest possible way. I'm just dividing n by all the possible factors to see if all the remainders are 0. And it's prime if it never has a 0 remainder. And here is a little test. Is prime using the Pascal versus is prime naive on this number 28,657. And if you run it, you can see that actually it is a prime number. This was on a list of large prime numbers. And I also told the computer, please time how long it takes. And you can think we did a really smart thing of doing this log business, but it's still quite a bit slower than just doing the naive thing. So we did all this work and we didn't get anywhere. And in fact, you might notice that at the end of the day, we're still working on up to the square root of n. So everything I've said so far is definitely true, but it is not actually that fast, because you still have to compute numbers up to the square root of n. And that is a huge number compared to log n. So we want to get an algorithm that is polynomial in the log of n, and computing things up to the square root of n is way too slow. So everything I've done so far is true, and it works, but it is too slow because you have to work with these really long sequences. When n is a really big number, this whole row will be really long, and that's too much work. So even though I've done log n operations, log n convolutions, every operation involves these long vectors, and that's too slow. And actually, they tell me that in the paper. So I could have skipped all this by just reading the paper. So they say, after they have the proof of this result, just like we did, they say, the above identity suggests a simple test for primality. Given an input n, test whether it's satisfied. That's what we were doing. However, this takes, so they use a big gamma, that means order n time, because we need to evaluate n coefficients in the left-hand side. So you always need to keep track of n coefficients. So I got away with square root of n, still just as bad. Here is, I think this is the actual genius part of the paper. Let me annotate some of this. Here is the actual genius thing they do. A simple way to reduce the number of coefficients is to evaluate both sides modulo a polynomial of the form x to the r minus 1. The original computation involves these long rows of size n, and they're saying, let's not compute the entire thing. Let's compute like a shadow of it. We will take the shadow of this thing, modulo some simpler thing. So we're going to simplify this big long row into something simpler. And what they actually do, it sounds very complicated. Mod, so they're saying take it mod. Let's make a little room to work here. So they're saying compute things mod x to the r minus 1. This is the big idea of the paper. And mod x to the r minus 1 algebraically looks kind of complicated. But if you remember what we're doing in Pascal's triangle, we're keeping track of these polynomials as just lists of numbers. And mod x to the r minus 1 means treat x to the r as the same as 1. And 1 is x to the 0. 1 is x to the 0. So every time you see something of the form x to the r, that is exactly the same contribution as something of the form x to the 0. And in Pascal's triangle, the 0th entry, the entry on the leftmost, is x to the 0. Then this one is x to the 1, and so on. So what does it mean to do x to the r is the same as x to the 0? It says pick some r. Maybe we'll pick r equals 5. 0, 1, 2, 3, 4, 5. And we'll get to this row. And this will be x to the r. Let's just write it here. X to the 5. So if r is 5, it's saying we're going to treat everything we get from x to the 5 over here as the same as x to the 0. And so what this means is that we're going to, instead of keeping track of this long, long row, which is order n, over here, we're going to keep track of just r numbers. So we're going down from n to r, and the way we're doing it is we're just gluing anything that happens after x to the 5, we just glue it back onto the beginning. So we're going to sort of get these first 5 numbers, 0, 1, 2, 3, 4, and that'll be added on to the next 5 numbers. So that'll be, it's technically it's 5, 6, 7, 8, but because we're treating x to the r as the same as x to the 0, those numbers will just get added on. So instead of having the numbers 1, 11, 55, we're going to have 1 plus 462, 11 plus 462, 55 plus 330, and we're just going to stack them on top of each other. And the nice thing is, when you stack numbers together, if it's all zeros, like that's what we're checking for, if it's all zeros. If it's all zeros and you stack it on top of each other, it should still be all zeros. If it's not all zeros and we stack it on top of each other, we can cross our fingers and hope that it works out to all non-zeros. And that'll be our check. So they've described it in terms of algebra. I've described it here in terms of looking at the Pascal's triangle. And they have a nice sentence about this. So they say, so in other words, we test if this is true, they're taking it mod x to the r minus 1. This is why they wrote it this way. It's really easy to write down. From lemma 2.1, it is immediate that all primes n satisfy this equation. So if you have a row of all zeros and you do the stacking thing, stacking it on top of itself, then for sure, it's still all zeros, you're good. The problem now is that some composites n may also satisfy the equation for a few values of a and r, and indeed they do. So there are some numbers where when you do the stacking thing, even though it was non-zero to begin with, you get kind of unlucky in the way you stack it, and things cancel out. So you have like a 1 over here and a minus 1 over here, and when you stack them together and add them up, then you get a 0 all of a sudden. So you fooled yourself into thinking it's all zeros. So that is the downside of what they're doing, stacking things together. So it speeds things up. You go from having to compute a vector of size n down to computing a vector of size r. That slows, that's a big speed up. The slow part of calculating n things is gone, but you have this new problem of maybe you fooled yourself. And so this is the genius, and this is why this is an Annals math paper, and these guys are like big time, this is a big result in the field of mathematics, is what they do in the next sentence. So however, we can restore the characterization. We show that for appropriately chosen r, if the equation 2 is satisfied for several a's, then n must be a prime power. So what they do is they say, we have a theoretical proof that even when you're stacking itself, even if you get unlucky, you cannot get unlucky for many possible values of a. So if you're going to get unlucky, it's not going to happen over and over again. You're going to eventually find a spot where you can check if it's actually prime or not. And so the other key thing is that they bound the size of the a and the r. So they say you only have to check r values up to log n. You only have to check a values up to log n. And by combining that, you can be sure that it actually works. So to recap, they started with this idea of looking for zeros in Pascal's triangle, and then they did this smooshing trick. Instead of keeping track of a row of length n, they smooshed it down to a row of length r. And then they proved using theoretical math that you can just use very small amounts of r. So r just can be logarithmic in n, and it will still work. So that's the idea. I did some kind of like bare bones implementation of this in my Python code. So if you want to check out exactly how it works, what I did is using this equivalency x to the r equivalent to 1, I made this condense function. And this takes a vector, which is maybe a long vector. So vec is a long vector, and it condenses it down into a vector of size r val. And how does it condense it down? Well, it just like loops through, and it repeatedly adds chunks of size r val to itself. So it's exactly what I showed over here. You start with the full row, and you just condense it down by taking the first 5 entries and then adding on the next 5 entries. Just add them right on top and do that over and over again. So you always do that, and you always take it mod whatever you're working in, mod n. And so then I have this function called generate nth row of Pascal's triangle, which is now super simplified. Instead of keeping track of a vector of size n or square root of n like I did, you can keep track of a vector of size xr mod and just keep that around to begin with. And you can use some small value. So here I did it with xr mod equals 14. There you go, 14. So by just keeping track of the first 14 entries and stacking everything else, everything beyond the first 14 just gets stacked into those 14 entries, I can do a check. And I didn't call it is prime, I called it could be prime. And that is because, like they said in the paper, right, this doesn't actually tell you for sure if it's prime. Maybe you got unlucky for this particular value of r. And to really check, you would have to check over all the r values and a values that they explain in this paper. So if you go to the paper, here is the full algorithm that they came up with. and they're saying you got to check all the R values up to R, where R is such that this is true. So you got to understand exactly what that means. And then A is up to this value. And the point is they're both bounded by log n. Okay, so this is the could be prime function. And here I checked it for a bunch of numbers and it works. And it is sometimes about the same speed as doing it the naive way. So as the numbers get bigger and bigger, the could be prime function should eventually be faster because the is prime naive scales with square root of n, but this XR mod thing goes by log n, which is supposed to be very nice. However, if you start to put in numbers that are so big that one would be faster than the other, so if you replace this value of n with the next bigger value of n, so this is a prime number I found on Wikipedia, it turns out that the whole thing breaks. So it thinks that it couldn't be prime, even though it is prime. And the reason is there's an integer overflow. So it's these numbers, by the time it's big enough to matter, it's so big that the implementation I have doesn't actually work anyway. So you know what? I tried. Anyway, that's a good place to end the video. I guess if you made it this far, congratulations, and you can make fun of me in the comments.